Okay, so we will continue our course materials regarding the electrical system in chemical plants. Yeah. Slide first. Okay, hopefully the slide is now visible in your laptop. Yeah. So as I mentioned before, that we will continue course materials regarding the basic electricity law. Yeah. So I will teach regarding the several concepts, yeah, and also the calculations of the power. There are one-phase and three-phase electricity or electrical systems, and also there is several circuit, yeah, in AC/DC circuit, whether it's resistance. We have the RLC, yeah, resistance, capacitance, and also inductance. We have RL circuits, yeah, and so on, yeah. And we will also learn for today regarding the single line diagrams, yeah. So consisting of the frameworks, yeah, of the electrical systems in the chemical plants. And lastly, we will learn regarding the options for supplying the electricity to the chemical plants. And lastly, we will also learn how or several examples, the real examples of how the chemical plants utilize the electricity. Yeah. Okay. So the first thing that I would like to give it to you is regarding the phase angle difference. Yeah, so the phase angle difference or phase angles can be actually defined as the angular component of the complex number representations of the functions. Yeah? So this notation is commonly used to represent an electrical impedance. So in this case, the phase angle is the phase difference, yeah, between the voltage applied to the impedance and the current driven through it. Yeah. So if we have a look through the graph, yeah, graph A, B, and C, and also the number in here, the systems, yeah, the systems of the electrical system consisting of the pure resistivity, pure inductivity, and also pure capacitivity, 1, 2, and 3 in here, yeah. So we can see that from the graphic, yeah, for the pure inductance, the currents is actually lags the voltage by 90 degrees. Yeah. So if you compare it, the blue line and also the green line, yeah. So there is actually the lags by 90 degrees, yeah, for comparing the current and also the voltage. While for the pure resistant, so the voltage and current is actually in phase, yeah. So there is no difference in here, yeah. While for the pure capacitance, the voltage lags currents by 90 degrees. Yeah. So we can actually try to match it. Yeah. So in here for the resistance, it's actually abbreviated to this number. Yeah. This system. So this symbol, I think Pak Hari already explained. Yeah. So this symbol is actually abbreviated or denoted as the resistance. Yeah. For this one, we call it as an inductance. Yeah. And also for this symbol is abbreviated or denoted as the capacitance. Yeah. This one is corresponding to the B, and this one is for the A graph, yeah, and this one is for the C. Yeah. Okay, so this is actually regarding what is actually the important thing of the phase angle. So the phase angles plays an important role, yeah, especially in electronics, yeah, where there is actually an involvement of the voltage and they call it various sinusoidal waves, yeah. So in electronics, usually the phase angles, yeah, refers to the numbers of the electrical degrees of lag, yeah, or lead between the voltage and current, yeah, as I mentioned before, yeah. So commonly it actually occurs in the AC circuit, yeah. Okay, so this is the another illustrations, yeah, to distinguish between the three systems mentioned from the previous slide, yeah. So for the pure resistance, or we call it in phase, yeah. So the values of the P is here is actually equals to 0 degrees, yeah. And for the systems, so this one is 0 degrees, yeah, for the system with the positive phase or denoted as the pure capacitive, yeah, here. So it's denoted as a positive phase, while for the pure inductive, yeah, so it denoted as the negative phase. Yeah. So this is the illustrations how we can distinguish between the resistive system, inductive system, and also the capacitive system, where the voltage and the current can be calculated by using this formula. Yeah, so for each system, so there are specific formula to calculate the voltage and also the current. Okay, so another thing that is actually very important, so we call it as Phasor diagrams. Yeah, so the Phasor diagrams can be defined as a graphical representations of the relations between two or more alternating quantities. Yeah? So for examples, in this case, we have the relationship between the current, the voltage, and also frequency, for example. Yeah. Or in other words, it depicts the relationship between two or more sinusoidal waveforms having the same frequency. Yeah. So based on the Phasor diagram data, so we can actually use the Phasor diagram in order to calculate the phase angles. Yeah. And the Phasor diagrams also can translate the rotation vectors into the diagrams on the X and Y axis. Yeah. So the illustrations is actually given in the left hand side. Yeah, so we can have a look that for the resistance, inductance, and capacitance, there is actually vectors, yeah, vectors for the voltage and also the current. Yeah, so in the case of the resistance pure or the pure resistance, we call it in phase. Yeah, so the current and also the voltage of the resistance is actually in the same directions. Yeah, with the we have also the omega values in here. Yeah, for all of the systems, we have an omega, the certain omega values, and for the inductance, pure inductance, we have the vectors of the voltage is actually, what do you call it? Graculus, yeah, or we have the degrees of the 90 degrees, yeah, in relationship with the current, yeah. While for the capacitance, pure capacitance, we have also the vectors of the voltage of the capacitance is actually, yeah, we call it Graculus in Indonesia, with the currents in here. But the difference is actually the directions of the vectors. Yeah, for the inductance, the directions of the vector of the voltage is actually going to the north, yeah, or going up, while for the voltage of the capacitance is, yeah, is actually going down for the directions. That's why in here the inductance, yeah, the inductance is actually called the negative phase, yeah, while for the capacitance is call it as positive phase. Yeah. Okay, so this is the examples how we can actually utilize the Phasor diagram operations, yeah? Or we call it as a complex number operations. Yeah. So for examples, in here we have two voltages, yeah, in the system. So we have a V1 and V2, where a V1 is 20 volts and also the V2 is 30 volts. Yeah. So we would like to determine or calculate the VT. Yeah? The VT in here we call it as a total voltage. Yeah? The total voltage is here is V1 plus V2. Yeah, with the angle phase in here is actually 60 degree. Yeah. So in here for V2, because it's in the horizontal line. Yeah. So we have the there is no yeah, we use the phase angle of 0 degree. Yeah, so we can just multiply for the horizontal components the voltage of the V2 multiplied by the cosinus of the 0 degree. Yeah, so cosinus of the 0 degree is equals to 1. So we get the horizontal component voltage of the V2 is 30 volts. Yeah, while for the vertical components we can just multiply the voltage with the sinus, yeah, sinus of the angle. Yeah, so we have the angle for the V2 is actually 0 degree. Yeah, and we have the voltage of the vertical component is equals to 0 volt. Therefore, for the V2, yeah, so it's equals if we write down this one in the forms of the vectors, yeah, so it will be equals to 30 plus 0j. Yeah, so or in here we can just make the general forms. Yeah, that the 30 in here is actually a V2 in the horizontal component plus the V2 in the vertical component. Yeah, j. Okay, and for the V1, so we have the horizontal component of the voltage multiplied by the cosinus of the angle. So we have a specific angle in here, yeah, which is actually 60 degree. Yeah, so we multiply the voltage with the cosinus 60 degree. Yeah, so cosinus 60 degree is half. Yeah, so that's why in here we have 10 volts. Yeah, while for the vertical component, we multiply the voltage with the sinus, yeah, of the 60 degree. Yeah. So we have in here 17.30 volts. So therefore, if we write down in here in the form of the vectors, yeah, for the V1, we have 10 plus 17.32 J. So in order to get the values of the total voltage, we can just use this formula, yeah, the square root. So this the Vt will be equals to the square root of the V1. Okay, so we do a sum up of the horizontal component, yeah, and the square of the horizontal component, yeah, which is actually this one and this, yeah, 30 plus 10 square plus 0 plus 17.32 square, yeah, and yeah, square root of the summations, we will get the values of the total voltage. Okay. So this is one of the examples how we can utilize the Phasor diagram, yeah, in order to calculate the total volumes based on the two quantitative parameters that is given from the problem. Yeah. Okay, so this is, yeah, another examples, yeah, of the Phasor diagram operations. Yeah, so we have yeah, for example, this one we have 4 factors. Yeah, sorry, it's still in Bahasa actually in here. Yeah. So we have 4 factors in here, which is A, B, C, and D. Yeah. So the concept is actually similar with the previous one. Yeah. So we can just do the summation. So it depends on what factors that we want to identify. Yeah, in here. So we can use. Yeah, I think you have also learned this factor materials, yeah, in calculus, yeah, how we actually sum up the factors, how we actually do the difference of the factor, yeah, between two factors, or multiplications of the factors, and also the divisions of the factors. Yeah, so this is just the general concepts, yeah, of how we can utilize the Phasor diagram operations. Okay, so another parameters that we want to or need to be considered, yeah, in electrical systems is actually, we call it as an impedance. Yeah? So the electrical impedance commonly defined as the measure of the total oppositions that a circuit or part of the circuit presents to the electric current. Or in this case, we can actually define it as the measure effective resistance in an AC circuit. Yeah. So the impedance commonly includes both resistance and reactance. So we can divide it, the impedance, with this formula, yeah, where Z is actually divided as abbreviated as an impedance, or denoted as the impedance, where the V and I in here corresponding to the voltage and current respectively. Yeah. And for the pure resistive system, we can divide it, the impedance, as this, yeah. So R plus J O, yeah. or we can just so the units of the impedance is similar with the resistance, which is actually in ohms. Yeah. So the difference is the impedance, as I mentioned before, is actually the mutual effective resistance. Yeah, in an AC circuit, or we can actually call it as the total oppositions that the circuit or part of the circuit presents to the electric current. Yeah. Another parameters that must be considered also the inductance and inductive resistance. Yeah, so in here, the inductance can be actually defined as the tendency of the electrical conductor to oppose a change in the electric current that is actually flowing through it. Yeah. So in here, the flow of the electric currents will create the magnetic fields. So in here, yeah, so will actually create the magnetic fields around the conductor. So the field strength depends on the magnitudes of the currents, yeah, and follows any change in the current. So in here we can calculate the inductive reactance in ohms, yeah, by using this formula where the XL equals to the 2 multiplied by the T multiplied by the frequency, yeah, and also the inductance in henries, yeah. So the units of the inductance is in H, yeah, or we call it as the henries, yeah, henries unit, where the frequency commonly called in the units of the hertz. Yeah? So the higher the frequency, based on this graphic, yeah, from the slide, we can see that the inductance will also increase. Yeah, thus the inductance resistance will also increase. Yeah. However, we can see that by increasing the frequency, the currents will be dropped, yeah, or decrease by increasing the frequency of the system. Yeah. So in here also we can actually define, yeah, the 2VF in here. So I think you have also learned in the physics, yeah, the basic physics. 2VF can be also defined as the omega, yeah. Or omega can be defined also the angle, yeah, the phase angle. Okay, so the circuits in the electrical systems can be actually classified into 3. Yeah, so the first one is we call it the resistor and inductor. Yeah, so in this case, the resistor or inductor, or we call it the RL series circuit, yeah, is connected across a constant voltage source. Yeah, so in here we have the voltage sources. Yeah, and yeah, so we can actually assume that for examples in here we have the resistance and also the inductance. Yeah, so the inductance denoted as the L and resistance is denoted as the R. Yeah. So if we have a look through the directions of the vectors here, yeah, so the voltage and the current in resistive circuit are both in phase, yeah, and therefore the vector R or divided as the VR in here, so it's drawn superimposed to the scale onto the current vector, yeah. So the VR and I is actually superimposed, as I mentioned before, yeah, in the beginning of the slides, that the pure resistive systems, we call it in-phase system, yeah, where the directions of the voltage is superimposed or similar with the current, yeah. While from the inductance, we can have a look through the directions of the vector, yeah. So the current is actually lags the voltage in the pure inductance system, yeah. Therefore, the vector VL is drawn 90 degrees in front of the currents and to the same scale as the VR shown in this figure. Yeah. So in order to define or calculating the voltage, yeah, or the total voltage or the voltage from the sources in here, yeah, so we can actually calculate it based on this formula. So we have the V square in here equals to the VR square plus VL square, yeah. Or we can actually use this one, the V equals to the square root of the VR square plus VL square. Or we can actually define also the VR and VLs as the current multiplied by the resistance, yeah, and current multiplied by the inductance, yeah. So, or in here we can also calculating the currents. Yeah, there is actually flow through the system. Yeah, we can actually define it as here. Yeah, so because we get it from this formula. Yeah, where the V will be equals to the I square R square plus XL square. Yeah, then we have V equals to the I square root of the R square plus XL square. So we can actually calculate or determine also the current. Yeah, that is actually flow through the systems or the RL circuit. Yeah. Okay, so we have the exercise in here, yeah, or the examples. Yeah, so we have this kind of the systems where the RLC circuit have frequencies of 50 hertz with the current flow through the systems 4 ampere. Yeah, and we have the resistance and inductance 30 ohms and 0.5 henries respectively. And we need to calculate the V, yeah, or the voltage in here. Yeah. So how we can actually calculate it? Yeah. So first of all, we can first calculate the impedance. Yeah. Because if you want to calculate the Vs, yeah, or voltage from the source, it's actually equals to the current multiplied by the impedance. Yeah. So what we have to do first, we have to calculate the Z, yeah, where the Z is actually equals to the R square plus XL square, yeah. And we need to define the XL. So what is the formula to calculate the XL? So the R is already given in here, yeah, which is actually 30 ohm. How about the XL? Based on the previous slide, what is the formula to calculate the XL? Anyone still remember? As a functions of the frequency.
2 pi f times L.
Yes, yeah. So Z equals to the R square plus 2 VFL. Yeah. Okay, so we have in here Z will be equals to the 30 plus 2 VF is 50 hertz, yeah, multiplied by the L is 0.5. Then we will get the Z values. Yeah, the Z values is equals to 159.8 ohms. Yeah, I have already calculated. Yeah. So once you get the Z values, yeah, you can calculate the voltage from the supplied voltage, yeah, or we call the VS, yeah, in here. The VS we got it from the current multiplied by the Z, yeah. So you will, the current is already given here for ampere multiplied by 159.8 ohms. Then we will get around 640 volts. Okay. How about the VR? What is the voltage of the resistance in here, or voltage resistivity? So we can just multiply the current with the resistance, yeah. So you can just 4 multiplied by 30, or you will get 120 volts, yeah. While for the VL, you can just calculate it also E multiplied by the XL, yeah. So 3 multiplied by V, so 4 multiplied by the XL is, what is the XL values? The XL values is based on this, yeah. So we have 157 ohm. Yeah, then we will get the VL values, yeah. So around 628 volts. Okay, so if you are asked to create the Phasor diagram, yeah, then how you can actually create it? Yeah, so I will give you an examples in here. Yeah. So we have a VR here, which is actually superimposed with the I, yeah, or the current. And we have a VL, yeah. So as I mentioned before, the VL is what do you call it? ya tegak lurus or create the 90-degree angle in relationship with the current, yeah. And for the Vs is actually in here, yeah. So you need to calculate the Vs, yeah. So once you calculate the Vs, which is 640 volts, yeah, and we have the VL is what is the VL value? 628 volts, and we have the VR equals to 120 volts, yeah. And how we can calculate the angle in here for the P, yeah. If we have in here the VR 120 volts, and we have the 628 volts of the VL, and we have the VS 640 volts, and how we can define the angle between this line, between the line of the VS and also the VR, or we call it the phase angle, yeah, the phase angle or P, yeah, in here. How do you calculate? Please remember how we can actually use the rules of the what do you call it, trigonometry, yeah, trigonometry. So we have the, for examples in here, we have the P, yeah. So, and as mentioned in here, so we have a P, we have the XL, we have the or we have a VL in here, yeah. For XL, we have the R, we have the Z, yeah. Then we will have the, for example, tangentials of the P, yeah, is equals to, anyone?
XL over R, sir.
Yes, good, yeah, XL over R, yeah. So we can just use the XL and R values, yeah. So the XL is actually 30 ohm. Sorry, the XL is actually, where is the XL? XL is all these values, yeah. So XL is 2 VFL or equals to the 157 ohm. Yeah, so we can calculate it based on the XL and R values, yeah. 157 ohm divided by the R, yeah. The R is 30 ohm. So the tangential P or the tangential of the phase angle is equals to, yeah, 157 divided by 30, so around 5 point something, yeah. Then we can just do the arc tangential, yeah, to get the values of the angle of the P, yeah, or the phase angle, yeah. Then we will get around 79.2 degree, yeah, for the phase angle. Yeah, so this one is 79.2. Okay, so this is one of the examples how we can solve, yeah, the problems in the RL circuit or resistor inductor circuit, yeah, or whether we can calculate it, yeah, the current, or calculate it the supplied voltage, yeah, as well as we can draw the Phasor diagram and determine the phase angle, yeah, in the RL circuit systems. Okay. Any questions until this point? Okay, so if there is no questions, assumes that you can out what I explained, yeah, so we can understand. Then I will continue with the second classifications of the circuit, yeah, we call it the resistor capacitor circuit, yeah. So the capacitive reactance of the capacitor will actually decrease, yeah, as the frequency across its plates actually increase, yeah. So it can be seen from here, yeah. So the capacitive reactance will be decreased as a function as increasing the frequency of the system, while the currents will be actually increase linearly increase, yeah, by increasing the frequency, yeah. So or we can call it the capacitive reactance is inversely proportional, yeah, to the frequency. Okay. And based on this graph, yeah, again, for the based on this factor, as I mentioned before, that the resistive pure resistive systems, it will the voltage will be superimposed with the current. Yeah, so that's why the directions of these two parameters is similar. While for the capacitive, pure capacitive, yeah, the voltage or the voltage factor or VC is actually drawn 90 degrees behind, or we call it lagging. Yeah, in here, lagging the current factor, or and to the same scale as VR as shown in this illustrations. Yeah. And we can calculate the capacitive reactance by using this formula, yeah, where the XC equals to 1 over 2VFC. So it's inversely proportional when you calculate the XL. Yeah. So for the XL, we have 2VFL. Yeah. But for if you want to calculate the capacitive reactance, yeah, you have to use this, yeah, this formula, or we can divide the 2Vf, yeah, similar as previous circuit. Yeah, 2Vf is equals to the omega. Okay. Okay, so another exercise. Maybe I'll try to give you around 5 minutes to solve it. Maybe, yeah. So after that, we will try to discuss it. Yeah. So please, you can calculate the current through the capacitor and resistive, capacitive, and supply voltage. Or in here, we can divide it as the VR, VC, and VS. Yeah. Okay, yeah. So based on here, we can yeah, just give you a clue that these values, yeah, is actually equals to the omega, yeah, because the voltage commonly, yeah, using for the generic formula, they use the, yeah, in here 100 sin omega t, yeah. So the 314 is actually the values of the omega. Yeah. So in here, the frequencies is not given. Yeah, so that's why the information that is given from these problems is the voltage as a functions of time. Yeah, but yeah, it's also a functions of the omega and also the time. Yeah, in here. Okay. So please calculate the current. Yeah, which is in here. We have the I. Yeah, as well as calculate the voltage, yeah, of the resistive, capacitive, and also the supply voltage. Okay, I'll give you 5 minutes maybe to do it, yeah, and we'll discuss it later. Okay, anyone finish? So what is the first step that we need to determine in here? Anyone can give a thought or an idea?
Find the value of Z, sir.
Yes, the Z values. How do you get it, Kevin?
Is it from the square root of R square plus XC square, sir?
Yes, square root of the R squared plus XC squared, yeah. Okay, so then how you define the XC?
XC is 1 over WC, sir.
Okay. So what values that you get from the calculations?
For the XC, I get 31.8, sir.
Yes, 31.8. Yes, so 1 over 340 times 1 to the 10 power minus 4. Yeah. Okay. Farad, sorry. So you will get 31.8 ohm. Yeah. Then you will get the Z values here. So the square root of the R square, which is actually 10 square plus 31.8 square. So it's around 33.4. Yeah. Okay, so once you get the Z values, what is the next step?
I think you can find the value of I, sir.
Yes, the values of I. How do you get it?
V over Z.
V over Z. Yeah? Okay. So in here, so the V values, yeah, the V values in here is actually this one, yeah. So the VT is actually V sinus, yeah. So this one is actually the VC, yeah. Sorry, the V values sin omega t, yeah. So we have 100 divided by 33.4, yeah. So you will get around 3 amps, 3 ampere, yeah. Okay, so what is the next step that you need to find in here? So you can find the VR, yeah. So once you get the I, you can calculate the VR, yeah, which is actually I multiplied by the R, yeah. So 3 multiplied by the 10, so 34, yeah. You can calculate also the VC, yeah. I multiplied by the XC, yeah. And it, yeah, is equals to the 95.6. And you can calculate also the Vs. So the Vs can be also calculated by using the formula of the trigonometric, yeah, because as I mentioned before, that the VR, yeah, so if you plot it in the Phasor diagram, yeah, so you will have the VR in here, you have a VC, yeah, then you have a Vs. Yeah. So the Vs can be also calculated by using the formula of the trigonometric, okay? So VR squared plus VC squared. Okay? Then you will get around 100 volts. Okay, so this is actually the way how we can calculate or solve the problems, yeah, to find out the current, find out the voltage of the resistivity, capacitivity, and also the voltage of the supply, yeah, in here. And yeah, another examples will be given in the following slide. Yeah, is there any questions until this point?
All good, sir.
Okay. Yeah. So let's continue. Yeah. So the last one for the type of the circuit, we call it the RLC circuit. Yeah. but the RLC in here is actually divided also into two. Yeah, so the RLC circuit, there is actually series in parallel. Yeah. Okay, so for the for the first classifications, we call it the RLC series circuit. Yeah. So in this case we have the so it's actually made up based on the three individual component voltage. Yeah. So we have in this system we have wait, how will use this? So we have a VR. Yeah. It's actually the voltage of the resistivity. VL is the voltage of the inductance. Yeah. And also VC is actually the voltage of the capacitance. Yeah. Okay, so based on this, we have actually the similar current. Yeah, so the currents is actually common for all these three components. Yeah, so the Phasor diagrams will therefore have the current vector as their reference. Yeah, so we can have a look in here. So the current is actually based as or used as a reference. Yeah, where again for the resistance in phase is actually we have the similar directions with the voltage here, and for the inductance and capacitance, yeah, as I mentioned before. So we have the negative and positive phase here. Okay, so in here, this means that we cannot actually simply add the VR, VL, and VC together in order to find out the VS here, because it's actually based on the factors that is actually being plotted with respect to the currents. Yeah. So that's why in order to calculate the supply voltage in here, yeah, so for the RLC series circuit, yeah, so we can actually use this formula, yeah. So Vs equals the square root of the VR square plus VL minus VC square, yeah. And we can actually have or calculate also the impedance, yeah, based on this formula. So we do not think about how we can actually derive or do the derivations of the formula. Yeah, just take it as it is. Yeah, so where the z equals the square root of the r square plus omega multiplied by the inductance minus 1 over omega times the capacitance square. Yeah, and we can actually define also the values of the p, yeah, or the angle phase in here. Yeah, so calculating based on this formula as well. Yeah. So it depends on the which parameters there is actually known. Yeah, so we can use that quantitative parameters in order to calculate the phase angle. Okay. Okay, so in order to make it understandable, so you can try again, yeah, to calculate this exercise. Yeah, so we have the R, L, and C are given, yeah, the specific values, which is 12 ohm, 0.15 henries, and 100 microfarad. Yeah, while we have the supplied voltage of 100 volts and with the frequency of 50 hertz. Yeah, in here we need to calculate the total impedance, calculate the total current, and also the power factor. Yeah. Okay, so please calculate it. Yeah, the power factor in here we can define it as the cos P. Yeah. Okay, so I'll give you another 5 minutes maybe to do it. Yeah, and let's discuss it later after 5 minutes from now. Okay, anyone finish? Okay, I just give you maybe the step-by-step how to do it. Yeah. So first of all, the step is almost similar with the previous circuit. Yeah, whether it's RL and also RC. Yeah. So first of all, we need to calculate the Z. Yeah. So the Z values or the total impedance. Yeah, can be actually determined for the RLC series circuit. Yeah, by using the formula that is given from the previous slide. Yeah, which is R squared or R squared plus XL minus XC squared. Yeah. Okay, so you need to calculate first the XL and XC. Yeah, and the XL you can get it from the 2VFL. You can get the XC from the 1/2VFC. Yeah. So the L and C values are known, and also the frequency also given in here, which is actually 50 Hertz. Yeah. So you can easily calculate it the Z. Yeah. And after you calculate the Z, you can calculate the I by using the Vs over Z. Yeah, Vs supplied voltage is actually given also from the problems, which is 100 volts. Yeah, and once you calculate the I, yeah, so total current is get it, total impedance also you get it. Yeah, the Z values. And how about the power factor? Yeah, so the power factor can be determined. Yeah, as I mentioned before, is actually cos P. Yeah, so cos P is equals to the R over Z. Yeah, because when you when you put the graphic, yeah, something like this. Yeah, so we have a P angle phase in here. Yeah, so we have the in here we have the R, we have the Z, yeah, and we have the L. Yeah. Okay, so cos P is actually the R divided by Z. So yeah, after that you can easily calculate it. Yeah, so the R values is known, which is 12 ohm, and Z values also get it from here. Yeah, so you can get the power factor. Yeah, the cos P value, and after you get it the cos P value, then you can get the phase angle. Yeah, just arc cos of these values. Yeah. Okay. Any?
Sure.
Yep.
So the power factor is the angle, sir?
No, the power factor is actually the values of the cos P. So cos P is actually the power factor, or we call it as a PF. Yeah. PF is power factor. PF is equals to the cos P.
Okay, thank you, sir.
Okay, no problems. So this is actually the power factor. Okay, any other questions for this exercise of the RLC series circuit? Okay, yeah, so I think hopefully it is clear. Yeah, so we can move on to the last circuit. Yeah, so we call it the RLC parallel circuit. Yeah, so previously we have the series circuit, but this one we have the parallel circuit. Yeah, so if we have a look through the schematic, yeah, of this circuit, yeah, so you can see that the supply voltage or the Vs in here is actually common to all three components. Yeah, wheels the supply current, which is actually Is, yeah, denoted in this circuit. Yeah, sorry, this one. Yeah, the Is is consists of three parts. Yeah, so previously we have the VR, VL, and Vs, but in the parallel circuit, yeah, the three components is actually the currents, yeah, instead of the voltage. Yeah, the supplied voltage is common for all of the resistance, inductance, and also the capacitance. Yeah, while the currents is different. Yeah. So the current flowing through the resistor, we call it the IR. The current flowing through the inductor, we call it the IL. And the current through the capacitor, we call it the IC. Yeah. Okay. Okay, so based on this, the total current can be drawn from the supply will not be mathematically just the sum up of these three individual branch. Yeah? So we can use this. I think this is actually almost the same with the previous one. Yeah, with the voltage. Yeah. So we have the VR square plus VL minus VC. Yeah, but in here we can just change the notations. Yeah, instead of voltage we use the current. Yeah, in order to calculate the in here supply current or overall currents. Yeah. Okay, so this is just the another examples. Yeah, so I think the steps is almost the same. Yeah, so you calculate the Z. Yeah, where the Z impedance can be calculated using this. Yeah, again the XL and XC values can be calculated. Yeah, using the XL is 2VFL, XC is 1/2VFC. Yeah, so L and C is given or are given in here. Okay, so you can calculate the Z values, and after that you can calculate the IS values. Yeah, in order to calculate the supply current or IS in here. So VS divided by the Z values that is calculated from using this formula. Yeah. Okay, so we have already learned several circuit types in the electrical system. Yeah, so we have the RL circuit, we have the RC circuit, we have the RLC series and RLC parallel circuits. Yeah. So the next one is actually the reactive power, or we call it the active power. Yeah. So what is the reactive power? Yeah, the reactive power can be defined as the portions of the power generated by the generator. Yeah, but it's actually cannot be utilized. Usually generated by the reactance components of the RLC circuits. Yeah. So we can have a look through the formula in here. Yeah. So where we have the Phasor diagram of the resistance and also the inductive reactance. Yeah, in here XL values. Yeah, and we have the impedance also in here where it's create the angle phase. Yeah, with a P. Yeah. So and also we can calculate it also or make the Phasor diagrams in the case of the power. Yeah, so we have the power active, power reactive, and also total power. Yeah, so reactive power, active power, and also the total power. Yeah. So what is the active power? So based on this schematic of the Phasor diagram, we can calculate the angle phase by using this formula, whether we use the tangentials of the P, cosinus of the P, using this approach, whether it based on the left hand side Phasor diagram is actually XL per R, but it will be also equals to the reactive power divided by the active power, based on the right hand side of the Phasor diagram. And the same thing if you want to calculate the cos P or the power factor. So as I mentioned before, that cos P is actually power factor. Can be calculated by using this formula. So R divided by the Z. Or can calculate the power factor by dividing the active power divided by the total power. So in here, the total power can be also formulated using this. So the voltage multiplied by the current. Whilst the active power can be calculated by using this. So the P total multiplied by the power factor. So the difference between the total power and also the active power. So the active power, there is actually the power factor, in the calculations or determinations. Or we can also using this formula. So where the active power can be calculated by using this approach. V square multiplied by the cos square of T divided by R. Okay. Okay, so this is just the example, yeah, how we can actually know here. So if in the problems or in the informations, the specifications is given something like this, yeah. So for example, the AC motor with the specifications of the 1 kilowatt slash 220 volts cos P equals to 0.8. So indicates, so this actually indicates this 7 points, yeah. So the first ones, the motor works at the voltage of 220 volts. Yeah, the active power is actually 1000 watt, yeah, or 1 kilowatt. Okay, the power factor, so it's actually equals to the cos P. Yeah, so this is actually the power factor, which is 0.8. Yeah, so if the power factor equals to 1, it means that the power factors equals to the power, total power. Yeah, so if the cos P equals to 1, it indicates that the power factor, or no, it indicates that the active power is equals to the total power. Okay, so commonly the power factor is, yeah, less than 1. Yeah, whether it's, yeah, is commonly ranging from the 0.6 until 0.9. Yeah. So another point is the motor provides active power which rotates the motor axis and continues to load equals to 1000 watt. Yeah, so which is actually classified as this, yeah, 1 kilowatt. And the motor consumes the total power of this, yeah. So P total is actually, total power is equals to the active power divided by the power factor, yeah. So which is, in here we have 1020, 1250 volt ampere, yeah. And the motor returns reactive power to the main source by reactive power, yeah. And in the form of the factors, we can put, or based on the Phasor diagram, yeah, we have this illustrations of the Phasor diagram. So we have, in the x-axis we have the active power, and the y-axis we have the reactive power, whilst this line, yeah, is actually corresponding to the total power. Yeah. So the P can be calculated using this, yeah, because cos P is given, yeah, cos P equals to 0.8, then we will get the P, yeah. P is actually R cosinus of the 0.8, which is actually 36.86. Yeah. Okay. So we have an exercise in here. Yeah. So please try to determine, yeah, the current and also the voltage of the AB and voltage of the BC based on this schematic. Yeah. So you need to find out the VAB and VBC, yeah, as well as the current. Yeah. So if in here is given the voltage of 220 volts of the voltage of the AC. Yeah. So the VAC is given, and also the R1 and XL are 10 ohm and 40 ohm respectively. Yeah. Okay, so I'll give you 5 minutes to do it. Yeah, and we'll discuss it. Yeah, after 5 minutes from now. Okay, I think it should be very quick, yeah, because all of the parameters are actually given in here. So can you tell me what is the current that you get from the calculations? Anyone get it?
5.33, sir.
Okay, good. Yeah. So the current is 5.33 is from VAC divided by the Z. Yeah. So we have the VAC is actually 224. See here divided by the Z is actually given also in here 41.23. So we have 5.334. Yeah. Okay. Okay. And once you get the current, it will be very easy to calculate the VAB and also VBC. Yeah. Just this one multiplied by the R. Yeah. And VBC we can multiply by the inductance. Yeah. Okay, so the R is given. Yeah, so 5.34 multiplied by 10, you'll get 53.4. And we have also the XL. Yeah. So you get, yeah, so it should be very easy, yeah, to do it, yeah, for this case. Yeah. So if you want to check whether this calculation is correct, yeah, so you can just double check it, where the VAC values, yeah, is equals to the VBC square plus VAB square. Yeah. So whether this one, the result is 224. See? So if the result is this, yeah, so it means that your calculation is correct. Okay. Okay, so move on to the next example. Yeah, so we have another examples in here. So if it is known, I think this is still the RL series. Yeah, but there is another points that is emphasized in here is actually to calculate the phase angle and also the average power consumed by the solenoid. Yeah. So if it is known from this problem, yeah, so the R is given 30 ohm and the inductance given also 200 millihenry and also the frequency of 50 hertz. Yeah. So you need to calculate first the impedance, yeah, which is actually Z. Yeah, so the Z will be equals this, because this one is RL series. Yeah, so you can calculate it using this formula. Yeah. To calculate the impedance, sorry, yeah, it's heavy rain in my home, so if my voice is not clear, please let me know. Yeah, so I'll try my best to make it more clear. Yeah. So for the current through the solenoid, so you can calculate it, yeah, using this formula. While the phase angle, yeah, so you can calculate it based on the. It is better to use, yeah, cosinus tangen is up to you, yeah, as long as yeah, I think is the results must be the same. Yeah, so you can calculate it based on the known parameters given from the questions. Yeah, so the cos P in here is actually calculated by using this. Yeah, and average power, yeah, the average power can be also denoted, yeah, as the active power. Yeah, the average power consumed by the solenoid, we can define it as the active power. Yeah, where the active power can be calculated by using the formula of the total power multiply by the power factor. Okay, the total power is V multiplied by the I, yeah, or voltage multiplied by the current, yeah, and the power factor is the cosinus P. Okay, so you will get the average power consumed by the solenoid. Okay, until this point, is there any questions from the students?
All good so far, sir.
Okay, good. Yeah. Okay, so we can just move on. I think this one, I think I get it from the exercise from Pak Heri's book. Yeah, so you can try to have a look through it. Yeah. So I think I forgot which latihan. Yeah, I think, yeah, you can just have a look through it. Yeah. So if you have any questions, please let me know later. Okay, so we'll move on to the next materials. Yeah, so we call it the three-phase electricity. Yeah, in here. Yeah, so the three-phase electricity is one of the alternating electric current. Yeah, that commonly used, yeah, in the electrical system. Yeah, so in here, instead of we using the phase one phase, yeah, so the three phase is actually can be also used, yeah, with different, yeah. So we have in here we have three different phases, yeah, phase one, phase two, and phase three, yeah. With there is actually a lagging, yeah, of 120 degrees for each phase, yeah. So why the three phase electricity is chosen, yeah, in several applied chemical industries, for example, yeah. So the reason for using three-phase electricity is the three-phase circuit provides greater power density, yeah, than compare it with the one-phase circuit, yeah, with the same amperage, yeah, and the size of the transmission cables can be minimized, yeah, and we can keep also the wiring size as well as we can lower the cost, yeah, or make it more cost effective, yeah. So in addition, the three-phase power makes it easier to balance the loads here, and also minimizing the harmonic currents, as well as the need for the large neutral wires. Okay, so this is the three-phase. So for the three-phase electric circuit, yeah, it can be actually divided into three. Yeah, so the first one commonly used in the generator. Yeah, so the difference in the phase angle between the currents passing through each wire determines the balance of the electric currents of the Y circuit used. Yeah, so for the shapes or the for the load, yeah, so for the three-phase electric circuit, yeah, so it can be classified into generally into two, yeah. So based on the load of the Y and load of the delta, yeah. So load gamma and load Y and load delta. So this one is actually means the forms of the electrical system, yeah. So in here we have the, for examples, yeah. So for instance, in here we have the Y shape, yeah. So what, that's why we call it the load Y, because in here in the electrical circuit or in the electrical circuit systems, it actually forms the Y shapes, yeah, or the Y forms, yeah. So we can calculate the VF and also the VFF, yeah. What is the VF and VFF is given, yeah, in the notes in the below side, yeah. So the VF can be defined as the voltage between one phase to the neutral, yeah. So we have in here the neutral phase, yeah, and we have in here another, yeah, another phase, yeah. So the VF is actually the voltage between one phase to the neutral conditions, yeah. While for the VFF is actually the voltage between one phase and another phase, yeah. So in here, for example, we have the phase of the T and S, yeah. So the distance between this phase, we call it, or we have the VFF, yeah, or the voltage between these two phases, yeah. Okay, so for the load Y and load delta, so we can actually find or have a look through this graph here. So we have actually the load of the Y denoting as the forms of the Y shapes, yeah, in this electrical system, while for the load of the delta, so the shapes will be something like this, yeah. So there is actually possibility to transform, yeah, from the Y load to the delta load. I will give you later, yeah, the explanations, yeah. And in this case, we can actually calculate also the power, yeah. So the total power can be defined as this, yeah. So the total power, sorry, the total work, yeah, the total works can be defined of this formula, where the total power equals to the 3 multiplied by the VF multiplied by the currents multiplied by the power factor, yeah, or the cos P, yeah. Or we can actually use this formula as well, yeah. If in the problems the VFF is given, then we can use this formula instead of this. Yeah. Okay, so for the Y load and also the delta load, yeah, so we can calculating the current, yeah, the current for each type of these classifications, yeah. So for instance, in here, yeah, for the Y load, yeah, so we have the, if the R and X are the pure resistance and inductance, yeah, so we have in here the R, yeah, and also X, yeah. So of each phase, yeah, so then we can calculate the current flowing through each wire by using this formula, yeah. So the I equals to the VF, yeah, divided by the R square plus X square, yeah. While for the delta load, yeah, so if we assume also the R and X in here, the pure resistance and inductance of each phase, then we can calculate the IA, IB, and IC, yeah. So in here, we can conclude that for the Y phase, yeah, the current is common, yeah, the current is common for each wire, yeah. I is common for each wire. While for the delta load, yeah, so we have in here the currents is different, yeah, for each wire. So denoted with yeah, the IA, IB, and IC that can be calculated using this specific formula. Yeah. Okay. So what is the advantages and of each type, each classifications of the load? Yeah. So for the loading of the delta, generally can handle larger currents, yeah, and it exhibits more efficiency than compared with the load of the Y, yeah. And the second one is protections for simpler delta configurations, yeah. And the last one is usually need to handle loads that are relatively heavy than the Y load, yeah. So the loads of the loading of the electricity demand in this case, yeah, so it's relatively heavy compared with the Y load, yeah? While for the loading Y, usually is preferably for electricity distribution, yeah, so from 3-phase to 1-phase, yeah. And it's actually less insulations requirement compared with the loading of the delta, yeah. Okay, so we can do the transformations as well, yeah, to convert the resistance, yeah, from the delta network to the Y network, yeah. So by using this formula, yeah, so to find out the RA, you can divine the by using this formula, yeah, RA, RB, and RC, so respectively can be used using this, yeah. So if you want to transform from delta to the Y load, yeah, so you can use this formula. While to convert from the Y load to the delta load, you can use this kind of the formula, yeah. And I will give you the examples later on, yeah, in the next slide. So for example, this equivalence, so you need to find the equivalent resistance, find out the equivalent resistance between these two terminals, yeah. So we have kind of the two terminals in this electrical system, yeah, where it gives the specific resistance for each terminals, yeah. So how we can do the transformations, yeah, in here. So first of all, we can make it, yeah, this form into the delta form, yeah. So delta form. So in here, from the rectangular form, we just transform it into the delta form, yeah. So it must be actually the same. I mean, the meaning is actually the same, yeah. So we have these two delta load, yeah. So how we can transform it into the Y load, yeah. So first of all, we need to denote it, yeah. So the RA, RB, RC, yeah, as well as the X, Y, and Z, yeah, in here, yeah. So RA, RB, and C is denoted in here, yeah. And we can just make the Y loads here in here, because we would like to transform on the in the bottom parts of the terminals into the Y load, yeah, from the delta loads, yeah. And we can calculating the R1, R2, and R3, yeah, in here by using the formula given from the previous slide, yeah. So we have these values, yeah, later 1.25, 1 ohm, and 1.66, yeah. And finally, we will get this, yeah. So R1, R2, and R3 is divided as this, yeah. So this is actually R1, R2, and R3, which has been calculated by using the transformation formula, yeah. And finally, we will get this kind of the electrical system, yeah. So we have this, yeah. This is actually the parallel system later, yeah. So these two is summations in the series form, yeah. And later on we will get this, yeah, in the parallel, yeah. So we can just do the inversely summations of these two resistance, and we will get the equivalence of the resistance of this, yeah, 4 ohm. Yeah. So if you would like to find the equivalent resistance, the way how we do it is something like this, yeah. So this is one of the examples how we can transform from the delta load into the Y load, yeah, by using the approach of the formula, transformation formula given from the previous slide. Same thing happens if you would like to transform it from the delta to the from the Y load to the delta load. Yeah. Okay, so until this point, any questions?
I think it's okay, sir.
Okay, yeah. So if there is no question, I think I will end up until this point. Yeah. So for the next following meeting, yeah. So on Wednesday, I will continue with the patterns of the electricity supply in chemical plants, as well as the real examples of the utilizations of the electrical power, yeah, in several chemical industries, especially in Indonesia. Yeah. So hopefully it should be enough for the 1 hour lecture on Wednesday. Yeah. So yeah, I will end up the course for today. Yeah. So thank you very much for your attentions. Yeah. And oh yeah, I would like to give you a reminder that I think OM3, yeah, will be held on next Wednesday. Next Thursday, sorry. Next week on Thursday. Yeah. So please be prepared, and we will try to make a coordinations with the lecturer's assistant, yeah, to give you tutorials, yeah, for the preparations of the module exam 3. Yeah. Okay, so if there is no more concern or question from the students, I'll end up the course for today. So thank you once again for your kind attentions, and we'll see you again next week on Wednesday. Yeah, so stay safe and healthy, everyone. Bye-bye.
Thank you very much, sir.
Thank you, sir.
No problems.